All right, let's dive into one of the biggest hangups for pretty much every Go developer at some point: arrays versus slices. Nailing this concept is absolutely fundamental to writing clean, fast, and bug-free Go code. So let's clear it all up.
Okay, the absolute best way to get this is with a simple analogy. Just think of an array as a fixed box. You order a box with 6 slots, you get exactly 6 slots. That's it. A slice, though, is totally different. It's more like a movable window. And the key thing here is that the window doesn't hold the items, it just gives you a view of them. In this table, man, it just lays out what that really means in practice. Look at that assignment row. When you pass an array to a function, you copy every single piece of data inside it. That can be incredibly slow. But with a slice, you only copy a tiny little header. That right there, that single difference, is a massive reason why slices are the default go-to choice for almost everything in Go.
Okay, so that flexibility is great, but it can feel a bit like magic, can it? Especially since we just said a slice doesn't actually store the data itself, so how in the world does it pull that off?
Well, it's not magic, but it is a really clever bit of engineering. It all comes down to this tiny little structure called the slice header. You can think of it as the brain, or maybe the command center of the slice. It's a small blueprint that tells the slice everything it needs to know.
So inside that little header are 3 crucial pieces of information. First, you've got a pointer, which just points to where the real data lives in something called a backing array. Second, it's length. That's how many items you can see right now. And third, it's capacity. This last one is the secret sauce for performance. It tells us how much the slice can grow before it has to do some heavy lifting. To really hammer this concept home, I love this analogy. Think of a slice as a train ticket. The pointer tells you which car your ticket starts at. The length is how many cars your ticket lets you walk through. And the capacity? That's how many cars are left on the whole train, starting from your car. See? The ticket isn't the train, it's just your access to it.
So if multiple slices can be like having multiple train tickets for the very same train, this leads to a super important question for any developer, right? What are the side effects? What could possibly go wrong?
And here it is, the first big gotcha. And trust me, it gets everyone sooner or later. Changes are not isolated. When you make a slice from another slice, they are both pointing to the exact same underlying data. So if you change an element in one, you've just changed it in the other, because they're looking at the same spot in memory.
But honestly, if there's one thing that causes the most headaches, the source of those really subtle, frustrating bugs, it's the built-in append function. It seems so simple on the surface, but its behavior can be wild.
See, append has this split personality, and it all depends on that capacity we talked about. If there's enough room in the backing array, it just slots the new data in, sometimes overwriting things you didn't expect. But if there's not enough room, it has to go build a whole new, bigger backing array, copy everything over, and then points your slice to the new location. 2 totally different outcomes. Okay, enough theory. Let's look at some actual code and see this in action. Because this is where this whole thing goes from an abstract idea to a very real problem in your codebase.
Okay, let's trace this. We start with 5 numbers. Then we create a subslice that contains just 2 and 3. Now here's the key. Its length is 2, but its capacity is actually 4, because it can still see the 4 and 5 in the original array. So when we append 99, Go says, hey, there's room, and it just puts 99 in the next available slot, which happens to be where the number 4 was. And bam, the original slice has now been mutated. This is the overwrite surprise, and it's a classic Go bug. This exact behavior leads us to a classic interview question. And it's not a trivia question, it's a test to see if you really understand how to write safe, predictable code in Go.
So what's the answer? You have to take control. You have to explicitly isolate your data. The only 100% guaranteed safe way is to create a brand new slice and use the built-in copy function. This makes sure your new slice has its own separate backing array. The connection is broken and the surprises are gone. So, now we know how to write correct code. Let's switch gears and talk about how to write fast code, because how you manage your slices has a huge impact on performance.
Remember when we said append sometimes creates a new, bigger array? Well, that process involves allocating fresh memory and then copying every single element over. It's a costly operation. To keep this from happening all the time, Go's smart about it. For smaller slices, it just doubles the capacity each time it needs to grow. This avoids a bunch of small, slow reallocations.
And yep, you guessed it, this growth strategy is another prime topic for a technical interview. Knowing this shows you're thinking about performance and memory, not just about making the code work. This slide just says it all. On the left, appending in a loop like that triggers multiple, expensive reallocations and copies. But on the right, we use the make function to tell Go up front, hey, I'm going to need space for 1,000 items. By pre-allocating the capacity, that whole loop runs with 0 reallocations. The performance difference here isn't small, it's massive. Okay, one last pro tip, and this one is subtle but so important. Imagine you have a slice with 1,000,000 elements. You take a tiny sub-slice of just 5 elements from it. Well, that tiny little slice is still holding a pointer to that entire 1,000,000-element array, keeping it alive in memory and preventing the garbage collector from cleaning it up. That's a classic memory leak. The solution? Just copy those 5 items into a new, small slice.
Whew, we have covered a lot of ground here, from memory models to performance gotchas. So let's just boil it all down to one simple, actionable rule you can use in your day-to-day coding.
The rule is just this. Always prefer slices. It's the standard, idiomatic way to do things in Go. The entire language is designed around them. They're flexible, they're efficient to pass around, and all the standard libraries expect them. It's the Go way. So when on earth would you ever use an array? Only in a couple of really specific, pretty rare cases. If you absolutely need a collection that can never change size and you want the compiler to enforce that for you, or if you're doing some super low-level stuff where you need precise control over memory layout. For 99.9% of us, 99.9% of the time, it slices all the way.
So the real takeaway here isn't just use slices. It's understanding that hidden machinery, the pointer, the length, the capacity, and that shared backing array. That's what lets you move from just writing code that works to writing code that's correct, fast, and safe. So before you pass a slice around, always ask yourself that question on the screen. Is making a safe copy essential here? Knowing when and why to do it is the key to building truly solid programs in Go.